Hello and welcome to InterSpeech and this first session on speech signal analysis and representation. My name is Hueber and I'll be co-chairing this session with
Benjamin Elie.
Yeah. For the remote audience, you can ask questions in the questions and then we'll read the questions to the speakers. Otherwise, you can raise your hands when that option is live, and you'll be given the stage remotely. For the audience in here, raise your hands, and you'll be asked to move to the up to the stage, so the remote audience will see you when you're asking questions. Okay, without further ado, let's move on to the first paper. A benchmark of dynamical variational autoencoders applied to speech spectrogram modeling, and it will be presented by Xiaoyu.
So shall we start?
Yes, please.
Okay, just click this, right? Okay, so thanks everybody. This is Xiaoyu. Today I'm going to present our paper, a benchmark of dynamical variational autoencoder applied to speech spectrogram modeling. So let me first give a brief introduction to the variational autoencoder, and then we will go to its dynamic extensions. Basically, a variational autoencoder, or a VAE, is a typical generative model where the observed data X is assumed to be generated from the latent variable Z. So the computation of the conditional probability P theta X depend on Z is the generative process, or we can also call it a decoder in the VAE. And normally this decoder is defined with a deep neural network. So let me give an example. So if we assume that this conditional probability is a Gaussian distribution, then the input of the deep neural network is the latent variable Z, and the output would be the estimation of the mean and the variance of this probability. So the main objective of the VAE is try to find a decoder that could maximize the data probability P theta X. However, due to the high nonlinearity of the deep neural network, it's intractable to directly compute the P theta X for parameter estimation. So instead of it, one could actually decompose these log probabilities into two terms by introducing a variational approximation of the posterior distribution. This is Q phi of the Z depend on X. We could say that the second term is a KF divergence, so it is a long negative. So, and in this case, the first term L could be a lower bound to the log probability. So instead of maximizing the log probabilities, the VAE choose instead to maximize this lower bound. And we also call it the evidence lower bound in the VAE. So for the training, this variational inference is implemented with an inference network where the input is the observed data X and the output is the parameter estimations of the latent variable. And we can also call it an encoder in the VAE. So basically, generally, a VAE models can be trained by cascading this encoder and the decoder and maximizing this evidence lower bound with respect to the parameters of encoder and the decoder. So what will happen when we go to a sequential data, like a speech signals? One of the major limitations of the VAE is that it processed all the vector pairs, the xt and zt, independently. However, we could know that there is the correlation between the frames for sequential data. So the VAE is too simple. In this case, we reviewed the recent literatures about extensions of VAE to time sequential data, and we group them into a new family. We call it the Dynamical VAE, or DVAE. So the DVAE is a generalization of the VAE to correlated sequential data. In the right figure, here, we give a graph model of DVAE with all possible dependencies. But in practice, we could simplify this graph model by omitting some of the dependencies, and you get a practical DVAE model. And for the training, the DVAE model can be trained with the same methodologies as the VAE. So just cascading the encoder and decoder and maximizing the evidence lower bound. Then we will talk about more details about the DVAE family. So first, we give a unified generative equation for a DVAE model. So here, for every time frame, the XG is generated from a sequence of latent variable Z, and it also depends on its previous observation, the x1 to t minus 1. Besides of it, we can also build a generative model for the latent variable ZT, where it depends on its previous states and also the previous observation. In the below, we list all the DVAE models we have reviewed in our paper. By unifying all their generative equations, we could say that actually each of them can be considered as a simplification to the unified generative equation. Then we will give two examples of the DVAE with more details. So let me start with the general formulation of the generative function. So it's the complete DVAE generative function. Then we give some simplifications. In the left figure, we simplify it into a classical state space model like a generative model, where for every time frame, the XG is only generated from the ZT, and the ZT is generated from its previous state, the ZT minus 1. And for the right figure, we make it more complex. So besides of it, for the generation of XT and ZT, we also give the dependencies to the previous observation, the x1 to t minus 1. Then when it comes to the posterior, we can apply this operation to identify the dependencies for the ZT. So this method can be find more details in the book of the Bishop. Inspired from the structure of the posterior, one could design the inference model by respecting the structure of the true posterior distribution. So here, for the left part, the ZT will be inferred from its previous state ZT minus 1, and also the current and future observation. So in there will be the XT to capital T. And for the right part, the ZT will depend on the whole observation. So it's x1 to capital T. Actually, the left column is the mode of DKF, which was proposed by Krishnan in 2015. And the right column is the mode of the SRN, which was proposed by Fraccaro in 2016. So before going to lecture session, there was one more thing to be noted, that actually the DVAE family can be divided into two categories. So we call it the non-autoregressive DVAE and autoregressive DVAE. So for non-autoregressive, the observed data x will only be generated from the latent variable z. So it can either be a single latent variable zt or a sequence of the latent variable. And for autoregressive DVAE, it can have both dependencies on its previous observation. So normally it will depend on a zt minus 1 it will depend on xt minus 1 or x1 to t minus 1. Then we will go to the experimental parts. In our paper, we built a benchmark on the analysis-resynthesis of speech signals. We use a dataset from the Wall Street Journal. We choose 3 subsets of them, and each of them will contain different speakers. All the audio signals are sampled in 16 kHz, and we normalize them by their absolute maximum value before feeding into our pipeline. Then we apply a STFT transformation with a 32 millisecond sign window and a 16 millisecond hop length. Then we crop the magnitude spectrogram into a 150 frame sequence during the training. So in summary, we have 9 hours for training, 1 hour and a half for validation, and 1 hour and a half for evaluation. To be noted that for the training and validations, we applied the cropping for the case of the batch training, but for evaluations, we don't have such rate, so we can fit the whole magnitude into the DVAE model. we evaluate the performance of all our reviewed DVAE models and also the VAE with three metrics: the root mean square error, the pascal value, and SGY value. So for the RMSE value, the lower is better, and for the two others, the higher is better. The first message we can get from this table is that the all DVAEs can outperform the vanilla VAE, which proves the correctness of introducing the time correlations to the speech modeling. Then we'll see more details about model structure. So we have introducing the autoregressive and the non-autoregressive structures. And for in this table, we could say that generally, an autoregressive model can be more powerful in speech analysis-resynthesis. And in the previous two examples, their inference models are designed by respecting the true posterior distribution. But in practice, some of models will not follow these rules. And in this benchmark, we could say that actually it's rewarding to do that. Normally, generally, we will have a higher performance. And we've also, the last thing we want to compare is the dynamical model on the ZT. This is because for the vanilla VAE, the prior distribution of ZT is assumed to be an identical independent distribution. So usually it's a zero mean and the unit variance distribution. But for DVAE, we could actually create a generative model for ZT. And in this paper, we could say that, yeah, it's really better to apply such a dynamic model on the ZT. So in total, the SRN performs the best because it features all the three properties as mentioned above. Here is the conclusion. So the DVAE model is of great potential to model speech signals. So if you are using the VAE nowadays, you can absolutely try the DVAE in your applications, and you can imagine you can get a better performance in your own work. And for the one who want to have a quick try of the DVAE models in speech modeling, we have made our code available to the public. So all the DVAE models are re-implementations of in PyTorch based on their source code and the paper presentation. And if you want to design your own DVAE model, you may try to think about the three properties during your design. So whether you want to use an autoregressive DVAE or non-autoregressive, whether you want your inference model respects the structure of the exact posterior distribution, and whether you want to apply a dynamical model on the latent variable. So in this paper, we mainly discuss about the experimental performance in our paper, but we have another review paper that will discuss more about the equations and the model structures, and you could find on the archive. And also, we also applied DVAE models into an unsupervised speech enhancement. You can also find it in the archive, which is called unsupervised speech enhancement using Dynamical Variational Autoencoders. So thanks for your attention, and feel free to ask questions.
So thank you. We're open for questions from the audience here or remotely. Yes. Can you please walk up to the chair over there and take the microphone and ask the question from there?
Can the latent variable ZT be given a phonetic interpretation? And did you try to manipulate the ZTs in any way?
Mm-hmm. No, we don't have this work on the phonetic explanation, but we just build reconstructions in our benchmark. But this could be a very interesting work in the future work.
Other questions? I don't see any raised hands either. Let me ask you a question.
Yes.
Regarding the family of DVAEs.
Yes.
Are there big differences in complexity, computational complexity in training and running them?
Yes, there exists the difference, But this will depends on the graph model we have showed in the slides, and it also depends on the implementation we use. For example, if we want to model the recurrency, we can either choose a LSTM, a RNN, or even a transformer like this. So the complexity will differ within different implementation. And also, that depends on, because we have a lot of the recurrent structures in the models, and some of them can be shared for the encoder and decoder. So if we choose to share some, for example, if we want to model the previous observation of x1 to t minus 1, both in encoder and decoder, so we can either build two independent recurrent blocks for encoder and decoder, or you can share them. So that will also will affect the complexity of the model.
So did you observe any dependency between performance and complexity? Like, was the best performing DVA the most complex one as well?
Actually, we did that experience, but not show in the paper. But we don't see much difference, because sometimes a complex model can have higher performance, but sometimes a simple model can have higher performance. But what may affect is that what we think is the graph model will affect most.
Okay, thank you. Is there? Yeah, there's a question remote. So let's see if we can bring that online. It seemed to disappear. Okay, you can read.
So there's a question from Evgen Karolov. When you reconstruct the signal, do you use phase component from the original signal?
Yes. Yes, we use the original phase.
Okay.
Okay. Any further questions?
Okay.
Does it work?
Hello.
Hello.
Did you encounter the posterior collapse problem with the DVAE architecture?
Yes, that's a very good question. But I think this is a common problem in the VAE, and I also think it will exist in the DVAE. But in our paper, we mainly focus on the dynamical modeling of the VAE models. So I think for the KI collapse, I think it's more like how you build your encoder or how you can add more constraints on your model architecture. So I think it's another work, but yes, it's a very interesting work.
Okay, thank you.
Thank you.
Last question.
No, there's no. It's the same question.
Okay.
Just like.
All right.
Okay.
Thank you, Albert.
Okay, so